Today I want to talk about a really important idea in group theory, and that is groups acting on sets. And in some ways, this is the correct way to think about a group. And what I mean by that is a group is not really this set together with some sort of description of how to combine elements from the set. It's really a set of things that act on another object. And that other object, well, can be distilled down to most generally a set, or sometimes else a vector space, or maybe a shape, so on and so forth. So anyway, let's look at the underlying definition here to get an idea of what we're talking about. So a left action of a group G on a set X is a map that will take from G cross X to X. And we're going to think about this as taking the ordered pair Gx to G dot X. So that dot is the action of the element of the group to the element of the set. So what should happen here is that the element of the group should act on the element of a set and give us a new element from the set. And of course, this should happen in a way so that the group operation is somehow preserved. Now, what do we mean by that? Well, we mean that these following two rules must be satisfied. If you take the identity element from the group and you act on any element from the set, you should not change that element from the set. So I think that kind of makes sense. The identity element of the group doesn't do anything inside of the group. That's the definition of the identity. And so if it is naturally acting on a set, it should also maybe not change the set either. And then, well, we should also have this kind of preserve the group operation. So what I mean by that is if we take two elements from the group, we'll call them G1 and G2, and we first combine them and then act on an element from the set, that should be the same thing as taking the element of the group on the right, acting on the element of the set, and then after that, acting on the element G1, again, from the left. So again, these two things should be the same. It shouldn't matter whether or not we first combine the elements of the group and then act on the set, or do it kind of one at a time. And then, well, in order to really talk about group actions, I'd like to recall a couple of definitions that you've maybe seen before. And so given any element G from a group, the conjugacy class of G is simply all what, for lack of a better term, conjugate multiples of G. And what I mean by that is it's everything of the form HG H inverse as H runs through every element from G. So like I said, all conjugate multiples. And now here's a very, very quick observation, and that is if G is in the center of the group, remember the center is everything that commutes with everything in the group, then the conjugacy class is simply the singleton. And that's because in this case, HGH inverse will just be G, and that's because again, G is in the center. That's the definition of being in the center. Now, the centralizer is another idea we want to talk about, and this is a subgroup. So the conjugacy class is most likely not a subgroup. Notice if you have a non-identity element from the center, then you've got the singleton right here, which is not the identity. But this idea of the centralizer is a subgroup, and you've probably seen the centralizer before. So we'll denote that by C underscore G and then a little g in parentheses. That's the centralizer of G in G. And that's going to be everything in G, which we'll call H, that commutes with this single element G. So in other words, GH is equal to HG, or in other words, HGH inverse is equal to G. So these two things look similar, but they're not the same at all. So if these look a little too similar for your liking, I would maybe pause the video, take your favorite, maybe small non-abelian group, and calculate the conjugacy class of some elements and the centralizer of some elements to notice they are not the same. Okay, so now let's look at some examples of group actions, and these are all pretty natural. So Sn acts on the set 1, 2, 3, all the way up to n pretty naturally. Notice that Sn is just the permutation group of this set. So it acts just by operation of the element. So we could write that generally like this. So we could take sigma in Sn and act on m, and that just becomes sigma evaluated at m. Now we could do an example as well. Let's take maybe the element 1, 2, 3 inside of S3, and we'll, for instance, act on 2. And so that's going to give us 3. And that's because if we evaluate this cycle at 2, it sends it to 3. And then, well, another example would be D4 acting on this set 1, 2, 3, 4. And we can build this natural action by looking at the square over here where we've labeled the vertices 1, 2, 3, 4, and maybe we've labeled the most general reflection, the generator reflection, if you will, to be reflection about this line. Then, well, what do we have? So for instance, if we take S and act on 2, that'll give us 1. And that's because S acting on this whole square flips it across that line. It takes 2 to 1. Then also S acting on 4, for instance, takes us to 3. Whereas R acting on 2, what's that going to do? So R acting on 2 is going to take us to 3 because it does a 90-degree rotation, we'll say counterclockwise. And then, of course, you could calculate some other things as well. Notice that SR squared acting on, for instance, 1. So what is that going to be? So notice that R squared is going to click this 1 over to the 3 location. And then S is what happens next. Notice that we're using this rule over here. And that's going to reflect across the line. So that's going to take us to where 4 is. So SR squared acting on 1 is 4. Okay, good. Then here's another example, and that would be GL2R. So that's going to be all 2x2 matrices with non-zero determinant. In other words, they must be invertible. And this pretty naturally acts on R2 just simply by matrix vector multiplication. So we could write out the rule for that. So ABCD multiplied into the vector XY. So if you remember your matrix vector multiplication, that's simply going to be AX plus BY in the first entry and CX plus DY in the second entry. Okay, so now that we've gotten our definitions taken care of and we've looked at some examples, let's start proving some simple results. So for our first little result, we're going to need another definition. I know there's a bunch of definitions here, but they are all necessary. So let's say we've got a G set X. So by a G set, I mean there's a G action on X. Then we say that X is G equivalent to Y, and we'll write this right here. So X tilde underscore GY, or just X tilde Y if there's no opportunity for confusion, if there exists a G in G such that Y is equal to G dot X. So these two things are equivalent if an element from G can take you from one of them to the other via the natural action. But then if we've got this equivalence, then we probably want to look at the notion of equivalence relation, and that idea here is what we'll call an orbit. So the orbit of little x is, well, we'll use this script O sub x, so it's going to be all y, where y is equal to g dot x for some g and g. In other words, it's the equivalence class of x under this equivalence relation, which is G equivalence. Now I'd like to point out that what we really need to do to even get this off the ground is prove that this is in fact an equivalence relation. That means that I can use all of those words up there that I've used while I was talking, like equivalence relation, equivalence class, so on and so forth. So let's do that here. But before we jump into the proof, let's notice that if we've got an equivalence relation, then we know the equivalence classes partition the set. In this case, the set is X. But the equivalence classes here are the orbits, so that means the orbits partition our set. Okay, great. So in order to show something is an equivalence relation, we need to show that it's reflexive, symmetric, and transitive. So let's do those one at a time. So reflexive is pretty easy, and that's just because, we see that x is equivalent to x because x is equal to e dot x, just by our rule over here. Then we need this thing to be symmetric as well. So remember, to show something's symmetric, you'll suppose that x is equivalent to y and hopefully end up showing that y is equivalent to x. Okay, so if x is equivalent to y, that means that there exists a little g in g where y is equal to g dot x. But now what we'll do is act on both sides by g inverse. So we'll have g inverse dot y will be equal to g inverse dot g dot x. But then by our rule over here, we can do the action one at a time or all at once by regrouping, kind of, if you will. So this is the same thing as g inverse g dot x, but that's simply e dot x, which is x. But check it out. What we have here is we have x is equal to g inverse dot y. But being equal to something from g dot y is exactly what we need to say that y is equivalent to x. So we started with x is equivalent to y and we ended with y is equivalent to x. Now let's show that this thing is transitive. And in order to do that, we'll suppose that x is equivalent to y and y is equivalent to z, and we'll hopefully be able to show that x is equivalent to z. But notice this means that there exists a g and an h inside of g such that we have y is equal to g dot x and z is equal to h dot y. So that's just rewriting those equivalences here using our definition. But now we're essentially home free because we can write z as h dot y, which is h dot g dot x, just replacing y here. But then we can regroup and we'll see that this is hg dot x. But again, that equation right there tells us immediately that x is equivalent to z. So we've got reflexivity, symmetry, and transitivity, which means that we in fact do have an equivalence relation. Okay, so now we're going to need a couple more definitions, as well as I want to look at an example of a group acting on itself, which is a pretty important action, even though it seems like it may not be before we really dig into it. So now let's look at the notion of a fixed point set and a stabilizer subgroup. So let's suppose we've got an action of g on x, which I guess we're going to have for the whole video. Then the fixed point set of little g in g, well, that's going to be a subset of x. And we'll denote it by x sub little g. And it's going to be all little x and big X, where g dot x is equal to x. So check it out. We're sorting through all of the elements of x and picking out all of the ones that are fixed under the action of this element from g. So now let's look at the kind of similar or parallel notion to that, or maybe dual notion to that in the subgroup side. And that's the stabilizer subgroup of an element x in capital X. And we'll denote that by g sub x, and it'll be all g and g, where g dot x is equal to x. So here we're kind of doing the opposite, if you will. We're sorting through all of the elements of the group, and we're picking all of the ones that fix this single element from the set. So let's look at an example. So let's take the group G, which is generated by 1, 2, 3, 4, 5. So that's going to be a 3 cycle and a transposition inside of S5. So that gives us a 6 element set, and I've written all the elements out over there. But I guess the important thing here is you can think about these as being disjoint. Maybe that's a natural thing to think about. This 1, 2, 3, well, obviously it just acts on the elements 1, 2, and 3. And 4, 5 just acts on the elements 4, 5 from the set that we're acting on, which is 1, 2, 3, 4, 5. Okay, so let's calculate some orbits, and then let's also calculate some, let's see, fixed point sets and stabilizer subgroups. So let's first look at the orbit of 1. So recall that the orbit of 1 is going to be what we get as we go through all of these group elements here and act on 1. So let's see, if we act with the identity on 1, we just get 1. If we act with this 3 cycle 1, 2 on 1, well, that's going to give us 2. If we act with this 3 cycle 1, 3, 2 on 1, that's going to give us 3. And let's observe that 4, 5 fixes 1, and then the other two act exactly like these 2, 3 cycles. So the orbit of 1 is this set containing 1, 2, 3. But we immediately know that that's also the orbit of 2 and the orbit of 3. And that's because the orbits partition a set, and we know that anytime you've got a partition of a set, the pieces of the partition only intersect if they're exactly the same. Okay, good. And then we could also take like 1, 2, or 3 as being the representatives, if you will. Okay, so anyway, now let's take x sub 1, 2, 3. So what is that? Well, that's going to be everything in the set that's fixed under the action of this 3 cycle 1, 2, 3. So I think that's pretty clearly just 4, 5. Because, well, 1, 2, 3, it does not fix 1, 2, or 3. It cycles them. And now we could similarly say, what is x 4, 5? So what are the things fixed by 4, 5? Well, that's going to be 1, 2, 3. And then I guess we could do x of just the identity element, and we'll get the whole set. I think that's pretty clear because the identity element fixes everything. We could also do x of the product of these things, 1, 2, 3, and 4, 5. But notice nothing is fixed under this element. So that would simply give us the empty set, which is okay. Now let's look at some stabilizer subgroups while we're at it. So let's look at G sub 1. So what's G sub 1? Well, that's going to be everything in our group that fixes the number 1. Well, notice that the identity fixes 1. That's pretty clear. And then this 2 cycle or transposition 4, 5 also fixes 1. But notice that's also the stabilizer subgroup of G2 and G3. Those are the two things that fix 1, 2, and 3. Okay. Now let's look at the stabilizer subgroup of the element 4. So that means we need to sort through all the elements of our group and pick out the elements that fix the number 4. So of course the identity is going to fix 4, and then this 1, 2, 3, this 3 cycle fixes 4, and then this 1, 3, 2, that 3 cycle also fixes 4. So we've got those. And notice this is exactly the same as the stabilizer subgroup of the number 5 as well. Okay, so now we're going to look at two little results, and then I promise we will get to groups acting on themselves, but we're going to look at showing that this stabilizer subgroup is actually a subgroup. I guess we need to show that. And then we'll also show that these orbits and these stabilizer subgroups are somehow connected. All right, so now we'll show that this stabilizer subgroup is a subgroup. I guess we shouldn't really have used the word subgroup over here, but now we're going to show that we could use the word subgroup. And in order to prove this, we're going to use the subgroup test, which is a nice one-step way of proving that something's a subgroup. Recall that H is a subgroup of G if and only if, for all G and H in H, G H inverse is in H. Okay, so let's get going. So let's suppose that we have G and H inside of G sub X. So what does that tell us? That tells us that G dot X is equal to X. Remember, being inside of G sub X means you fix X. And it tells you that H dot X is also equal to X. But notice if H dot X is equal to X, we immediately see that that X is equal to H inverse dot X, just by applying H inverse dot to both sides, if you will. Okay, cool. And now we're pretty much done. So notice that if we take GH inverse and dot that into X, then we can use our second rule over here for actions and write that as G dot H inverse dot X. And then just recall that H inverse dot X is X by that up there. So we get G dot X, but G dot X is X by this right here. So in the end, we get X. But the fact that GH inverse dot X was equal to X is exactly what we need for GH inverse to be in GX. Okay, great. Now we're going to prove a nice numerical result about the orbit and the stabilizer subgroup. All right, so what we'll show is that if G acts on X and they're both finite, it's important here that they're both finite, then the number of elements in the order is the same thing as the index of Gx in G. But let's recall how that's defined. That index of Gx in G is the number of left cosets of Gx in G. So that means, well, we should have a bijection from the orbit into the set of left cosets. So let's define what might be a natural map and show that that is a bijection. We'll call it phi, and it goes from the orbit of X to, and I'll call this L sub Gx, where that's going to be the set of left cosets. Great. And now how are we going to define it? Well, it's going to be a little bit of a process. So let's let y be in the orbit of X. So what does that mean? That means that y is equal to G dot X. Okay, but then I guess I should say for some G inside of G. Again, that's what it means to be in the orbit. And we're going to use this G to define our map. So we'll let phi applied to y be Gx. It'll be that coset. It'll be the coset with representative G. Now, let's recall that the set of left cosets, or left cosets, all have coset representatives. And those representatives are not unique. So what that means is that we really have to check that this is well defined even to get off the ground. Anytime your codomain is made up of things that don't have unique names, then you have to check something is well defined. Okay, so let's suppose using this rule right here that we have phi of y is equal to, I'll call it G dot Gx, and phi of y is simultaneously assigned via this rule to Hgx. Sorry, there shouldn't have been a dot here. That's not action, that's a coset. And then what this really means is that this for some little g in G means that we could have perhaps chosen two of them or something. Okay, anyway, let's see what this tells us. So if phi of y is equal to Gx, well then that means by our way we chose G up here, that y is equal to G dot x. But then if phi of y is Hgx, then by the way that we chose H here, that means that y is also H dot x. Okay, great. But now we can just like set those two things equal to each other and then multiply by perhaps like H inverse, and pretty quickly we'll see that H inverse G dot x is equal to x. But that's equivalent to saying that H inverse G is inside of Gx. But then if H inverse G is inside of Gx, that means that Ggx is equal to Hgx. Those two cosets are the same by a standard result about equality of cosets. But that means that, well, these two mappings really did the same thing, even though they seem like they might have been not doing the same thing. Okay, so we've showed that it's well defined. Now let's show that it's injective. So it's got to be well defined, injective, and surjective to be a bijection. So let's suppose that phi of y1 equals phi of y2. But that tells us what? That tells us there exists a G1 and a G2 in G such that y1 is equal to G1 dot x and y2 is equal to G2 dot x. So it may seem like the same proof of being well-defined, and that's because injectivity and well-definedness really are somewhat related. Injectivity is really like some sort of inverse map would be well-defined. That's why they kind of look the same. Anyway, so we've got this right here. But then if phi of y1 is equal to phi of y2, then what does that mean? That means that g1 gx is equal to g2 gx, because those are the outputs of those functions. And I guess I should say, well, how do we know that we're able to choose elements of the group here where making these equations? Well, that's because our domain is the orbit of x, and that's what it means for y1 and y2 to be inside of the orbit. Okay, so we've got this right here, but observe that means that g2 inverse g1 is inside of gx, I guess by coset equality again. But observe, that means what? That means that g2 inverse g1 dot x is equal to x, because being in g sub x means that you stabilize x. But then that means pretty quickly that g1 dot x is equal to g2 dot x. In other words, y1 is equal to y2. So there's where we get injectivity. We started with phi of y1 is phi of y2, and we ended up with y1 is equal to y2. That's how you show something is injective. Now let's show that it's surjective. And this is actually maybe the easiest one. So let's suppose we've got a coset. We'll call it gx, and this is in the set of cosets LGX. Good. But now all we do is we set y equal to g dot x, and then immediately we see phi of y is equal to the coset that we started with. Okay, so anyway, now we've got a bijection from OX to the set of left cosets, but that means that those two things have the same cardinality. But that means that this cardinality of OX is the index, because the index is defined to be the number of left cosets. Okay, so now for a big theorem, which is essentially proven already. All right, so here's a big theorem called the class equation. So let's say we've got x, which is a finite G set. Then we'll need this thing x sub capital G in order to write this down nicely. And that's just all x in x that are fixed by every element of G. Now we've got the class equation. So that says the number of elements in x is the number of elements in xg plus the sum as I goes from 1 to n of the cardinality or number of elements in the orbit of xi, where the xi form representatives from all of the distinct orbits. Now let's recall that this thing right here, this cardinality of the orbit of xi, is also the index of gxi in G, just for what it's worth. Now, how does the proof of this go? Well, it's actually fairly simple. First of all, equivalence classes partition a set. So that means the size of the set is simply the sum of the size of all of the equivalence classes. Now, orbits are equivalence classes. So look over here, we're like summing up all of the orbits. And then notice that if x is in xg, then the orbit of x is a singleton. So this gets all of the singleton orbits. So I guess over here, this is not all the orbits. This is with the orbit of xi not equal to xi. So it's the orbit of everything not in xg. Okay, great. Now what I want to do is look at groups acting on themselves a number of ways and look at the special case of this when a group is acting on itself. All right, so like I said before, groups can act on themselves a couple of different ways. Here are the natural ways. So via left multiplication. So that means that g dot x will simply be gx. So here, recall that the group is acting on itself. That means that x is an element of our group because our capital X is really just the group. Now, you can easily check that this left multiplication action satisfies these rules over here, so I'll leave that to you. It can also act by a type of right multiplication. So g dot x is xg inverse. And now why do we need a G inverse there? Well, check it out. Let's say we were to do GH dot X. So under this rule, that's going to be X times GH inverse, which is equal to X H inverse G inverse. Because taking the inverse switches the order of multiplication within the group, if you will. But now let's observe that this is G dot, let's see, XH inverse, just by our rule. But that in turn is equal to G dot H dot X, just working out from the inside. But notice that starting over here on the left and ending up over there on the right is what we need to satisfy this second rule. I guess I should say the first rule is kind of obviously satisfied. And then, well, conjugation is maybe the next natural action. That would be G dot X is equal to GX G inverse. And you can check this as well, although it's pretty much the same. You would just do GH dotted into X. So observe that's going to be GHX and then H inverse G inverse, where I skipped the step there and just went ahead and did the inverse. But now let's observe that that's going to be G dotted into HX H inverse. And then working from the inside, that's going to be G dot H dot X as needed. So that satisfies the rules for an action as well. Okay, great. Now I'd like to point out that in the case of a group acting on itself via conjugation, we get the orbit of X is equal to the conjugacy class of X. In other words, it's all so-called conjugate multiples of X as you run through the whole group, like we talked about before. Okay, great. So now let's see what we can do with the class equation and groups acting on themselves via conjugation. All right, so this is a really quick corollary to the class equation, just in the language of G acting on itself via conjugation. So just as a recall from what we just said, the orbit in this case, the orbit of X, is the conjugacy class of X. In other words, it's all conjugate multiples of X. And then the stabilizer subgroup of X, so by definition, that's going to be all G and G, where GX G inverse is equal to X, but that's exactly the definition of the stabilizer or the centralizer subgroup of X. Now we have the class equation. So the size of G will be equal to the size of the center of G plus the sum over all conjugacy class representatives, where the representative comes outside of the center of the index of the centralizer subgroup of Xi inside of G. Recall that this is going to be equal to the index of Gx in G, which is equal to the size of the orbit, which is equal to the size of the conjugacy class in this case. Now, I'd like to point out that since we're taking all of the Xi out of the center, this number is always strictly bigger than 1. And that's because all of the cases where the centralizer subgroup was the whole group, those ended up being in the center in the first place. Those are also the cases where the conjugacy class is just the singleton element as well. All right, so now let's look at some examples. Okay, so let's look at the example of S4 acting on itself via conjugation. So here's the class equation. But notice that this index here can either be calculated as the index or it can be calculated as the number of conjugacy classes of Xi by stuff that we talked about already. Now, in this case, it'll be easier to count the number of elements in the conjugacy classes. I think that'll be the case a lot of the times. Now, here's a quick description of how to write down the conjugacy classes for Sn in general. They are in one-to-one correspondence with the partitions of n. So the partitions of n are simply ways of writing n as an addition problem with non-increasing natural numbers, if you will. So here are all of the partitions of 4. So you can look up integer partitions if you want to see more of this. So observe that 4 can be written as 1 plus 1 plus 1 plus 1. It can be written as 2 plus 1 plus 1, 2 plus 2, 3 plus 1, and 4. Those are all of the partitions of 4. And then these correspond to the conjugacy classes. This tells us that all the cycles in this conjugacy class have length 1. And so in this case, that's just the identity. That's the only element of Sn in general where the size of all of the cycles is just length 1. I think that's pretty clear. And then this 2 plus 1 means that you've got a single 2 cycle and 2 1 cycles. So in this case, that just means you've got a transposition. So like 1 2, 1 3, 1 4, you could have 2 3, you could have 2 4, or you could have 3 4. So those are going to be all of the 2 cycles. Now this 2 plus 2 means that you've got 2 2 cycles. So that would be like 1 2 3 4. That would be an example of a product of 2 2 cycles. Notice they need to be disjoint here. I guess I should say this is all of the cycles being disjoint. You could have, let's see, 1 3 2 4. That would be an example, or 1 4 2 3. And I believe that's all of the examples of a product of 2 2 cycles. Then you could have 3 plus 1. So this is going to be everything that's a product of a 3 cycle and a 1 cycle. So in this case, you just get a 3 cycle. So like 1 2 3, 1 3 2. You could have 1 2 4, 1 4 2. That would be another example. Let's see. You could have 1 3 4 and 1 4 3. And then finally, you could have 2 3 4 and 2 4 3. So those are all of the examples of, let's see, the 3 cycles. And finally, you could have the partition 4, but that's going to be just a single 4 cycle. So let's see, you could have 1 2 3 4, that would be one way. You could have 1 3 2 4, that would be another way. You could have 1 4 2 3, that would be another way of doing this. You could have, let's see, 1 3 4 2, that would be one example. Let's see, you could have 1 4 3 2, 1 4 3 2. And then let's see, is that all of them? 1 2 3 4 5. No, I think we should have 6. So let's see, we could have 1 2, 1 2 4 3. That would be our last one. So let's count up the number of elements in all of these conjugacy classes. So we've got one element in this conjugacy class. That actually corresponds to the center. The center of Sn is always just the identity. We have 1 2 3 4 5 6 here. Let's see, we have 3 here. We have 1 2 3 4 5 6 7 8 here. And finally, we already counted here, we have 6. And so the class equation here is 24 equals 1 plus 6 plus 3 plus 8 plus 6. Okay, great. Now let's do another example like this. All right, so for our next example, let's look at D4. Let's recall that that's symmetries of the square. It has those 8 elements. And then, well, I think we all recall the multiplication rule here. Now the center, which is pretty easy to calculate, is simply the identity and then the 180-degree rotation. Now let's pick something out of the center and calculate its conjugacy class. So let's take R. So we need to look at all conjugate multiples of R. But we only really need to conjugate by a reflection, and that's because conjugating by a pure rotation, well, that's just going to fix R because R is going to, let's see, commute with all of the rotations. And so this would be the conjugate with S. Notice that S is equal to S inverse, so we don't really need to put an inverse there. Now, the rule is that we'll move S past R and it'll turn R into R cubed. So that gives us S squared, R cubed. But we know S squared is equal to the identity, so that's R cubed. And then, well, you can check conjugation with the other reflections as well, like, for example, SR, and you'll see that this also gives us R cubed. So in the end, we'll see that the conjugacy class is simply R and R cubed. Now let's move to something that is not in the center and not in that conjugacy class. Let's maybe take S. So now here, we don't really need to conjugate with just s itself, so we might as well conjugate with a rotation. So we'll do rs r cubed. We know that r inverse is r cubed, that's why we put an r cubed there. That's conjugating with r. So now we'll slide s past this r, and it'll turn into s r cubed. But notice that's going to be sr to the 6th, but that's sr squared, given the fact that r to the 4th is 1, because we're in the dihedral group. And so, well, that means that our conjugacy class of s must contain s, and it must contain sr squared. And then you can do some more conjugate calculations to show that that's it. I guess I should be saying here that the conjugacy class is always going to contain the representative we start with, because you could just conjugate by the identity. Now, what's the conjugacy class of SR? That should be the last thing here. So what we'll do is take the rotation, conjugate with SR, so that means we've got R, SR, R cubed, and you can do the calculation, but what you end up with here is SR cubed, meaning our conjugacy class here is SR and SR cubed. But now we've exhibited all of the elements of D4 inside of a conjugacy class, but that means that we've got our class equation. The size of D4 is 8, is 2 plus 2 plus 2 plus 2. Keeping in mind that this 2 here is the size of the center, and then these remaining 2's are the sum of the size of the conjugacy classes, or the orbits, or however you want to think about it, depending on which version of the class equation you take. Okay, good. Now let's do one more little application. All right, so what we'll show now is that if we've got a P group, in other words, a group of order P to the n, then the center is non-trivial. What do we mean by the center not being trivial? It means that it must contain more than just the identity element. Now I'm going to start with a little observation, and that is the index of G inside of the centralizer subgroup of really anything here is just equal to the size of G divided by the size of this centralizer subgroup. That's by Lagrange's theorem, I guess. But notice that since the size of the group is P to the n, we can put P to the n as a numerator. And then the size of a subgroup has to divide the order of the group. That means that the size of this has to be P to the k. But this is going to be P to the n minus k. But now this is going to be strictly bigger than 1 exactly when x is not inside of the center of G. Because check it out, if x is in the center of G, then this centralizer subgroup is just the whole group. But then this index is just 1. And also inside of the class equation, that would be all within the size of the center part. Okay, so now we can write down our class equation. So P to the n is the size of G, which is equal to the size of the center plus, let's see, the index of G, CGX1, or the index of the centralizer subgroup of X1 in G plus up to the size of G, or the centralizer subgroup of Xn in G. I guess I should use an M there because we used n for our exponent. Now, check it out. We know that this center can be just brought down. And then by our calculation up here, all of these are multiples of P. Now they're all bigger than 1 because they're, let's see, centralizer subgroups outside of the center. And we know that they're multiples of P just by this formula or calculation that we did, I guess. But since they're all multiples of P, if we take their sum, you get a multiple of P. We can just push them all together into MP. See what I did there? But now check it out. We've got P to the n here, a multiple of P. We've got MP here. That means that we've got the size of the center is Pn minus MP, but that has to be bigger than 1 because it's a multiple of P. But if it's a multiple of P, well, it can't be equal to 1 because that means that your prime would divide 1, which is a clear contradiction. But then if the size of the center is bigger than 1, the center cannot just be the identity subgroup or the trivial subgroup. Okay, so now let's look at a nice application of this to groups of order p squared. Okay, so now let's say we've got a group of order p squared, then we'll show that G is abelian. This is going to follow from our theorem. So by our theorem, we know that the center cannot be trivial. But the center is a subgroup, so it's a number that is not equal to 1 that divides p squared. Since p is prime, that means that the center is either p squared or it has size p. Now, if it's size p squared, then that means the center is the whole group and we have an abelian group. Now, if the center is p, then what does that tell us? That tells us that the quotient group G mod the center has order p. But then all groups of order p are cyclic. That's a result that is pretty standard. So that means that this quotient group, G mod ZG, is cyclic. Maybe we'll write it cyclic generated by the coset GZG. Now what we want to do is take two elements, I'll call it x, y, inside of G. But that means that x is inside of G to the m ZG, and y is in G to the n ZG for m and n natural numbers. That's because the cosets partition a group. I think that's well known. But then this means that x equals G to the m times Z1, and y equals G to the n times Z2, where Z1 and Z2 are in the center of the group. That's what it means to be inside of those cosets. But now we're essentially home free. We can take xy, which is equal to G to the m Z1 times G to the n Z2, and observe that G is going to slide past Z1 and Z2 because Z1 and Z2 are in the center. Z1 and Z2 are also going to commute because they're in the center. And then any power of G will commute with any other power of G just because they're powers of G. So everything in this picture here commutes. So putting that all together, we can write it as G to the n Z1, G to the m Z2. But that's going to be equal to y times x. But xy equals yx is what we need to show that this thing is abelian. But if this thing is abelian, then the center is not p, it's p squared. So we technically found a contradiction here, contradicting the fact that the center could have order p, meaning that the center had to have order p squared, meaning the thing was abelian to start with. Now, before we move on, and I guess all that's left is to leave you with some exercises, I'd like to point out that if G is equal to, or if G is a group of order p squared, then since it's abelian, we know from the fundamental theorem of finite abelian groups that that means that G is either ZP squared or G is isomorphic to ZP cross ZP. So that's cool. We know that if we've got a group of order p squared, it has to be one of those two. Okay, so now, like I said, I'll leave you with some exercises. Okay, so here are some exercises. The first is to compute all stabilizer subgroups and fixed point sets for a group being S4 acting on 1, 2, 3, 4. Or the group being D6 acting on 1, 2, 3, 4, 5, 6, where the action is motivated by the way that D6 acts on that hexagon there, where I've written the kind of canonical reflection. Next, let's find all conjugacy classes and the class equation for D5, S5, the quaternions Q8, and Zn, where n is arbitrary. Then I'd like to point out that for S5, probably writing down all of the conjugacy classes is a little bit too much, so you can just use a counting argument to calculate the size of each conjugacy class. And that's a good place to stop.